Okay, 3 steps to tuning SQL. First, you got to find the bad SQL. Second, sort of up to you, but the general practice is look at the execution plan. And third is to fix it. Well, how do we fix it? So step 1, how do we find the bad SQL? Often it's just a user calling up and complaining, right? I like to be proactive as a DBA, and so that's why I designed the Screen Enterprise Manager, the top activity. I love it. Maybe I'm a bit biased. But the idea is it shows a load on the database, and of that load, I can see the top SQL. And like green is CPU, and blue is I/O, and other colors are other weights. If I had a CPU starvation, I wanted to tune it. Well, there's only really one place to tune it, is that top SQL. I can see immediately there's a problem, or he's consuming all the CPU. So this is one way to find it. Another way is if you're an enterprise manager, we have these baselines. If I'm running a steady state OLTP load, I can capture it. And then enterprise manager will compare the current elapsed times with the baseline. So 3 ways to find bad SQL. And usually it's the user calling in. Okay. Well, okay, now I got a bad SQL. How do I tune it? Well, most Oracle books I look at say, well, look at the execution plan. I don't know about you. Personally, these things strike fear in my heart. I don't like reading these things. And that's just the tip of the iceberg. What if you do it? Anybody done a 10,053 trace? No. I talked about that. This is a 10,046. That's a 10,046, but 10,053, which tells us what the parser did and why, are super complex. So all this is complexity. My goal was to make it simpler. So we've identified the slow queries, we've looked at the execution plan, now we fix it. Well, how do we fix it? And I don't know about you, but this is what I see at customer sites is, okay, well, Oracle got it wrong, let's analyze the stats. Oh, it's still slow? Oh, let's run the stats again. Oh, it's still slow? Let's run the stats again. So, bad news. Okay. Here's an analogy. This rings true to me. This is from Google Maps, and this is directions from point A to point B. I don't know. I mean, this might appeal to a few people. Personally, I couldn't stand this. I want to see the map. So where's the map? Well, okay, cool. Here's the map. I know a little bit about New York City, not much, but I mean, here's Manhattan, right? I do know that I've flown in a few times. The airport's over here. So look, there's like a path from near the airport down into central Manhattan. Okay, that gives me some help. Now I have an idea of what my directions mean. But we're still missing something for optimization. Well, on Google Maps, you can see where the traffic is, right? So, red says there's a bottleneck, and green says it's flowing really well. My directions are taking me right through the bottleneck, but there's an optional route. So why don't I go use traffic? Bad way, good way. So what I would like with SQL is I don't want to see that just the execution plan or just the directions. I want to see the map, and I want to see where the bottlenecks are on the map. So before we get there, we're going to do a few things. We're going to look at how do we join 2 tables, how to do a multi-table join. Then we're going to go into how do we create a map, which is a VST or Visual SQL Tuning Diagram. And then once we have that diagram, we'll apply a methodology to it. How do we find an optimal execution path? And then we'll look at some examples. So when we're looking at a SQL tuning step, a SQL statement, probably the most important thing is knowing where to start. So it's basically, I look at it as a bunch of nodes, and we've got to go through all the nodes in the SQL statement. So where we start is going to have a huge impact on performance. But other questions come to mind is like, what indexes do we use, and what type of a join, hash join, nested loops, or merge join. The most important step is finding out where to start. But let's just step through some joins and see what happens or how we would approach them. So what do we do when index don't exist? What type of relationships are there between the tables? One-to-one, one-to-many, many-to-many, and then some special cases, outer joins and not exist. So this is just laying the groundwork. We'll get to the fun part in the middle of the presentation. But if I have 2 tables and I'm joining them on a column, join A and B on their ID, both have an ID column. Really, it doesn't really matter where I start. If I start at this table, I've got to go to every row and look at every row here. If I start here, I hit the same number of rows. Every row here is going to get combined with every row there. In a nested loops join, it doesn't really matter what order it is. my work's going to be rows in A times rows in B. If I did a hash join, it's a little bit different, but let's not go there yet. How about if there's an index? So same query, but now I have an index on table A ID and table B ID. In this case, if I start with table A, I'm going to have 8 rows, and I'll look them up with eight lookups. If I go the other way, I have 4 rows here. Each of them is going to be a lookup into the index, so 4 lookups. So clearly, we want to start with the table that has the least number of rows in that case. But this is something interesting I'll get to. When we get to the final solution state, it's not going to have anything to do with the number of rows in the table. It's going to have to do with the number of rows returned after a filter, which is our next slide. So this is a more typical query. I'm not just going to join 2 tables, all the rows. I'm going to join 2 tables with some filter criteria, predicate filters. So here I have a filter on table A, say where the field equals value A, and table B, field equals some value. Now, how do I join them in this case? What I want to do is look at the number of rows returned after I apply the filter. So if the filter on A returns 2 rows, then I'm going to have 2 lookups into B. But if I start with a B, and B had a filter, it's a smaller table, but its filter returns more rows than A, I'd be doing more work going from B to A. I'm going to start off with the least number of rows. That's going to determine how many lookups I do in the next table. So 2-table summary. If there are no indexes and no filters, then the order doesn't really matter, unless you're hash joining. If there are indexes, we want to start with the table, the smaller table. But usually we have filters. And in the case of filters, we don't care what the size of the table is. We care about how many rows are returned after we apply the filter. So the next part, I'm going to go into how sort of visualizing joins. There's a thing called set diagrams, which I think are pretty cool. But the diagrams are misleading, so I'm going to show a different way of drawing them. Has anybody ever seen this? Table A join table B? It makes it look simple, right? And then I thought this was really cool. There's a poster that's bigger than this. I'll get into it, but you know, our inner join or field one table equals field another table, not exist. Left join. I was like, wow, this sort of makes it easy to understand what's going on in SQL. And then we can add the sort of core inverses, non-exist A, right join B, so the opposite. And then in the middle, we can do the cross joins. So full outer join are the union of the 2 not-exists. So when I saw this poster, I said, wow, this is cool. I've always had a hard time imagining what's going on in queries. This makes it seem simple. But this is missing something important. So that this cool little diagram here for me is almost a non-existent paradigm. It does occur, but not that much. What this means is that we have a one-to-one relationship here. For the 2 rows, say found after the filter, I'm going to look them up in this other table. It's going to correspond to 2 rows. There are 2 sets. We're just talking about the overlap. Well, we're going to talk about visualization. So we're going to start building up how do we draw a map. So this one-to-one relationship we're going to draw this way. One-to-one, there's no crow's feet on either side. But what we see more commonly is not this cross-section, it's what I call projection. So if I have 2 rows in B, those 2 values can occur multiple times, one to many. This is a typical entity relationship. So those 2 rows are going to correspond to multiple rows in that table. So I'm going to project those 2 rows from B onto A. So this is one to many. This is how we're going to draw it in a map. And then this is why it sort of helps visualize why many to manys are so bad. If I can have many values in this table corresponding to many values in that table, I have cross multiplication or amplification. And then we're going to draw it with red, crow's feet on both sides, because these are sort of something to watch out for, a warning in our map. And now this stuff I don't think I'm going to go into too much. But what about outer joins? I personally have a really hard time remembering how outer joins work. So here's sort of like a cheat sheet. But in the map, I have an easier time of remembering it. The fatter side, so we're going to draw a little triangle in the middle of it. The fatter side corresponds to the table that has no rows being filtered out. If I find a corresponding row in B, great. If I don't, I'll probably return some field value. If I don't, then I'll return to null. But the number of rows returned to A stays constant either way. And then the other part of the map is, oh yeah, I want to throw this in here too. The maps can be interesting. If I have an outer join and it's a many to one, and I don't return any values from the this table in the outer join, this is the one that I sort of call like the translation. Maybe we're translating some ID into a value. But if that ID doesn't exist, we still want to keep the row. That's sort of what an outer join does. But if this table B doesn't return any values, there's no point in doing outer join. And this turns up, and then I can see this really quick. What I do is I mark it gray as a no fields are being returned from table B. So don't. This can just be locked off the query without affecting the values returned. Reading text, I find that really hard to see. Looking at the map, I find it easy to see. One thing to watch out for, and I don't think anybody would want this though, if the many to one relationship is flipped, if the many is on this side of the map, this can actually multiply the rows returned here, even though it's not returning any field values. This is usually a bug. So these are the kind of things I can see in visualization easy that are hard to see in text. So these slides will be up on the NoCOUG side, but the final thing is exists. This is how we're going to draw an exist. It's interesting to know that exist can be rewritten as a join with an in clause. And same thing, not exist can be done as a not in. So we'll have a little triangle in for a not exists. So what we're building up is the different visualizations in the map. So we have our outer join at the top, one to many to one, many to many, and not exist. With an in or an e would be an exists. And then we have the reverse. So now we're getting to the steps to actually draw the diagram. So we looked at the beginning of it. What we want to do is start where we have the least number of rows. If there's no indexes, that's a smaller table. If there are filters, predicate filters, then it's how many rows are returned after we apply the predicate filter. And then we're going to draw the map with these visualizations. So that's for 2 tables. What happens for 3 tables? It's interesting to know when there's a one to many relationship, who's the many and who's the one. Because if I join from a one to a many, and that one to many, what's going to happen is I can start off with 1 row, and I can pick up some more rows as I join into the many, pick up some more rows. My join set gets bigger. On the other hand, if I take 1 row from the many and join into the one, I'm going to stay up 1 row. One join from the next many into the one, I'm going to join 1 row. So my direction of join affects how much work I'm going to have to do. Now, if there's a filter, what if there's a filter on one of the 3 tables? Where do we want to start this join? I want to start where I can knock off some of the rows, because when I'm joining this way, if I'm picking up rows, I don't know the rows here. I don't know that they've already been knocked off here. So if I join this way, I have to wait to the end to find out these rows are knocked off. And I'm going to be building. I'm going to start off from 1 row here, build up some more rows, and then I have to look up for each of those rows. These guys. So I want to start where I knock off the rows soonest, because then I eliminate work going this way. What happens if what happens if the filter's on the middle table? This is where the one to many relationships come into. I have a filter here. Now I could go to the left or the right. I want to start with the filter because that knocks out some rows. It's the only filter, so I want to start there. But I want to go to the one so that I keep my running row set small. If I join down, I'm going to increase the number of rows probably, and then I'll have a bigger set to join back into the first table. And then if I have a filter on the top table, I have no choice. I start with filters. There's only one filter. I can only go one direction. So what we're trying to build up is decisions. Once we do have a map, how are we going to decide which directions to go on the map? And then finally, what if there's filters on all these guys? What do I do now? In this case, I'm going to need some more information. In the previous slides, I didn't need any information. There's one filter. I wanted to start on that filter, and I chose which direction to go, depending on whether it's a one-to-many relationship or not. So now what we're going to need some other information. What I'm going to want to know is what percentage of the table do these filters eliminate? And we can calculate that by the number of rows returned with a filter over the total number of rows in the table. And then the filter, the strongest filter, the one that eliminates the most percentage of rows, that's where we're going to want to start. Well, and so we did a 2-table join, a 3-table join. There's one thing really interesting if we get bigger. How about a 4-table join? The way Oracle works is it takes an initial table and it'll join one other table into it. So if I start off at that table, I can join in the next table, I get a result set, join in one more table, get a result set, join in one more table. I didn't realize that this is the only thing Oracle would do for a long time. I used to think, well, I could, same 4 tables, maybe I could join 2, and then join the result set. Oracle will never do that unless you absolutely force it to. Oracle's optimizer doesn't look for these paths. So that helps me know how do I come up with an optimal execution path. So now we're going to put it all together. So we've got our map and we've got a way to decide which direction to go on the map. So we draw, for each table we draw it as a node. We're going to, on that, once we draw all the nodes, we draw lines for each of the joins. For each of the joins, we want to draw a crow's feet where the mini is. And then we want to mark which tables have filters on it and which tables don't. So there's this book where this idea comes from, by Dan Toe, Sequelton. Anybody read this book? Cool. So, I mean, this is what the basis of these ideas are. So here's a query, substantial query. How would I tune it? First thing I do is I get a list of all the tables. These are going to be my nodes. Then I'm going to look through and get all the joins. These are my lines. And then I'm going to look for the filters in the query. And these are the nodes I'm going to mark that have a filter. So here I'm going to start drawing it out. So for each table I draw a node. And I like to do this in PowerPoint because I can take these things and move them around. Jonathan Lewis, when he uses this method as well. He likes to do it on paper, which I find a little crazy because then I have to erase and but PowerPoint's easy. So anyway, here I'm in PowerPoint, I draw my nodes. And then for each join, I'm going to draw a line between those tables that are being joined. Okay, I now have got a sort of a messy goop here. I can beautify it, but still this doesn't really tell me much. I mean, it tells me a little bit. It could be interesting. But I still don't have a way to tell me which directions to go. So here's sort of where the trick comes in. Not only is this a trick, but it also, for me, conveys the importance of having a well-structured schema relationship. Like if I don't define my one-to-manys in my database, my constraints, then the optimizer won't know either. It makes it more difficult for the optimizer. So what we're going to do is we're going to put the detail tables above the master tables. So this is going to have like a directed graph. So instead of just laying the nodes out willy-nilly, we have a pattern. So, okay, this guy here is order details, OD, and this is orders. So each order can have multiple details. I put the order details, above the master. And then we can do that. If this is a well-defined schema, I can go through all the tables, putting the details above the masters. And now I have a structured diagram. And with this structured diagram, we'll be able to find our directions for an optimal execution plan. But we're still missing one thing. We're missing the filters. So 2 of the tables have filters on it. I'm going to mark F with filter on it. But since there's one filter, that's where I would start. But there's two, so how do I know where to start? I need to add those filter ratios. So one of these conditions is on a user's name. You sort of have to go through and find out what's your typical data that would be inputted into this query. So it requires knowing what the bind variable values might be. So for a typical name, we eliminate, we only return 0.02% of the table on average. The other one's a date range. I have to know something about the application. For date range, we generally, in this application, return about 30% of the rows. So this filter is a lot more powerful than the one above it on a date range. So customer has a filter on name, orders has a filter on dates. So now with this information, that's all I really need to know to optimize this query. And what we're going to do is we're going to start at the most selected filter, and then we're going to join down when we can. If we can't join down, we join up. The reason we want to join down is because when I join down, I don't pick up any new rows. Stays my running row set size that I carry to each node will either stay the same size or it could actually get smaller. On the other hand, if I join up to a mini relationship, I'm going to expand the number of rows I have to carry to the next node. So it's sort of interesting to keep in mind in these diagrams. This isn't a rule, but generally the table on top is going to be the biggest. It's the main details. The ones below it are masters for that detail. It'll be a little bit smaller. The ones below it should be even smaller because they're the masters for these guys. This is not important, but it's interesting to keep in mind. So now we have our diagram. We have our structured directed graph. We have the two filters, and we have how strong the filters are. So what would be the optimal execution plan? With this, I think this is pretty awesome because with this, I can find out a plan in just a few seconds, basically. So the filter on C is more powerful than the filter on O, so I'm going to start on C. I want to go down if I can, but if I can't, I have to go up. So I join up to O. Remember, I want to go down if I can, so I go down to OT. I can't go down any farther, so I go up to OD. This is the foundation of the optimal execution plan. After this point, it really doesn't matter where I go. It might have some influence, but no matter who I join down to, I'm not going to change my running row set size. I'm not going to make it any bigger. I might make it smaller. But how would I tell Oracle to do this? I'm not saying that you should use hints, but if I'm trying to figure out whether Oracle's doing the right thing or not, I will want to give it a hint to see if my path is better than what Oracle does. And how do I test my path? I can test it by putting a hint leading with the aliases of the tables that I want to access. It's pretty cool. For me, it's sort of like Pac-Man. It's like you start at the strongest filter and you go to the next best prize, which would be the next strongest filter. So I don't know, can you guys read this out there? So here's a massive query, right? We've drawn all the one-to-many relationships, the biggest detail on top, and we've drawn all the filters. So these are the filters. Anybody want to guess on where to start? T7? So we start in T7. Now where do we go? T13. T13. Now where? T12. I should time this. Now where? Now where? Next? Next? 11. Next? 15. Next? Next? Oh. The left, which one? 4. 5 or 4?
4 to get you to 9.
Now which one?
9.
Now?
5.
Are you sure? 5? 3. No. 3.
Oh, 3.
Because that had a filter. There's a filter over here. There's no filter over here. Okay. Now, I think that was around 60 seconds. Maybe it was 120 seconds. I don't know. That we picked an optimal execution plan. What if we guessed? 355 trillion guesses. So, I think this is a pretty awesome way to find out an execution plan. But there's more. Hold on to the seat of your pants because it can show you some other cool stuff. So here's a query. I personally hate reading queries. I mean, and there's a bug in this query. Now, I can visually see it right away. Anybody have an idea what it is? This is the map.
That's
It sort of stands.
yeah, it's a Cartesian.
Look at the. There's no line in here. What happens when there's no join defined? Cartesian. So in the visualization, I can see that right away. Now, some of you might say, oh, I could read that query in a few seconds and figure out there's a Cartesian join. I personally couldn't. It just takes me a while to buffer all the data. But how about this one? You won't be able to get this one. Anybody know why, if there's a problem here or not? The diagram is, for me, the diagram helps massive. You can't. I'll tell you right now, you can't figure out the problem from the text. You have to get it from the diagram.
Your client should be related to client transaction.
So client and client transactions have relationships. Yeah, because this broker has two details, and if those two details aren't related, what does that mean? It's a cross product. So this is like, I call them implied Cartesian. Now I can see that from the diagram immediately. I can't get that from the text. In order to get that from the text, I have to go into the I have to either know about the data or I go into the data dictionary and find out their relationships. This is actually miswritten SQL. The guy who wrote it wrong. But I can see there's a problem immediately in the diagram. Okay, so far we've been talking about what I call well-behaved queries. The queries that we tuned, the one that we did in 60 seconds that had 355 million options, tabs, that was all the tables were one-to-many relationships. Well, what happens when we have many-to-many? And many-to-many might not even be many-to-many. Many-to-many might be that there's no constraints defined in the database, therefore we don't know as a DBA or even as an optimizer. If I'm optimization code, I don't know. If there's no constraints defined, that means that there could be a many-many relationship. And when there's a many-many relationship, we multiply the rows together. And unfortunately in life, there's lots of cases of this. So the example from Dan Tao, where he had a nice structured diagram, great. What if I didn't know the relationships? If there was no restrictions in the database, then as far as I know, there are many-to-many relationships. Then my nice, neat diagram that I had a path through becomes a jumbled mess. How do I navigate this guy? So here's an example. And the cool thing is we're going to take this and give it to Oracle and see what happens. So these are the same tables with the same indexes drawn graphically. In one case, there is a uniqueness defined, so I know who's the many, who's the one. In the other case, the indexes are non-unique, so I don't know it's many relationships as far as I know. So on the first side, on the left-hand side, there's a filter, right? So where do I start my query? Start with filter. Now where do I go? Down. And then I have no choice. I have to go up. That's the optimal plan. Now the next one, okay, cool, there's a filter on B, but now where do I go? I don't know. Do I go to A or C? So here's the query. This is in Oracle. It did 58 logical reads. It's a small data set. All I do, I didn't change any of the data, I just added a constraint. And now Oracle does the same query in 7 logical reads. That's the only change I made. So not only is it difficult for us, it's difficult for the optimizer. Although the optimizer has an easier time with it than we do. So what can we do as far as creating these visual SQL diagrams? We need to add some more information. And the piece of information we're going to add is the two-table join result set. So what I'm going to do is, and again, this is brute force attack. This is not, in order to get the solution, I've got to pound on the database. So this is not kind of stuff I would do on a production database. But if I have a copy of it, I'm going to brute force attack the query to get the information I need to optimize the query. So what I do is I pull off the subquery and I run it. The join from B to C only returns 1 row. The join from B to A returns 51 rows. Now, when I say brute force with a tiny query like this, who cares? But we're going to use the same brute force attack on some really big, massive queries. So now I start with my one filter, I know where to go. Where's my result set going to stay small? It's not going to affect this 1 row. So, but if I went from B to A, I'm going to take 51 rows and join it into C. A lot more work. So I start where the join set size is the smallest. Okay, now I'm going to go into some real life brutal queries. And these are queries that actually came from customers live in the field. So the first query ran for 24 hours and never completed. We kill it. And this is what I'd love to think. If you want to mess around with the query, like I'm gonna tune the I'm gonna try a different execution plan and then run it. Well, if it takes days to run, how fast can I iterate through it? And this is why I think the brute force attack is sometimes necessary. The brute force attack on this query took about an hour. And with that, I was able to get an optimal execution plan. The second is a really messy query with outer joins and scalar subqueries. And then the last one, we'll talk about how to force Oracle to do something it wouldn't do on its own that's optimal. But in order to force Oracle to do something optimal, I have to find out that that optimal path exists. So here's the first query. I don't know about you, but if I come to the office at 8 in the morning, my manager's like, tune this thing. I'm like, oh, there goes the whole day, right? And then we can look at the execution plan. I don't know if that helps you. It doesn't help me. But here we're going to create a visual SQL tuning diagram. Now, if I have to do this thing by hand, it is going to take me probably an hour to do it, right? I worked at Embarcadero. Part of the tool there, DB Optimize, will do it automatically. And this diagram actually comes from DB Optimize. But the query looks pretty complex. But one thing I'm going to do is this is a subquery. And this subquery, I just tried it out, and it ran in 9 seconds. Remember, this is a query that doesn't finish, the whole query doesn't finish in 24 hours. But if this runs in 9 seconds, that's telling me that this isn't a problem. And somebody noticed that, very observant. So these tables get joined together, and then these tables get joined together, but there's no join between them. This is something I wanted to improve in the product, but this is a union. It's not a Cartesian product. It's a union of these two. So, but anyway, this complex subquery is not a problem. So what I do in the tools, I just double click on it, and it classes it. So we can like zoom in on where the problem could be. So there's 3 filters, right? 1, 2, 3, and then these 2 filters on either side return 99% of the table. That's basically the whole table. So basically they're worthless. This filter in the middle only returns about 2% of the table. So this is where I want to start. Now where do I go after that? Probably the best thing to do is go from A to C, so 1 to many. I can see the returning roll set is 85,000. Going down, it's a mini and many, but it's much smaller returning row set than the other joins. But basically, all I have to do at this point is give Oracle a hint. Start at A, and it gets the query right. Now, why was it taking 24 hours to run? The reason it was taking 24 hours to run or more, didn't even finish, was for some reason, and I didn't investigate why. I probably need to do a 10,053 trace and figure out why. But it was starting at table E and joining to table C. And this table, that green number on the top is the number of rows. So it only had 5,000 rows, 5180. And the other one had 3 million rows, 3921080. What's the return set between the two? 198 million. So I have to, after I join these 2 tables, I have to take 198 million rows and go to the next node. Extremely inefficient. So not only can I find the optimal execution plan quickly, I can also see why Oracle is failing. And one thing that always drove me crazy, and still drives me crazy, is one of these is the optimized plan, and one of these is the problem plan that Oracle chose in the beginning. If I want to compare them to see what was Oracle doing wrong by comparing the execution plans, it's really different. It's not like comparing C code where like somebody added 1 line. You're like, oh, there's the 1 line. With an execution plan, like, joins down here show up here, things get all jobbled around. It's like impossible to compare them side by side. What I really want is I want 2 maps. I want this map is the same as that map. And the only difference is I can see here's one path, and then here's the other path. So the maps are the same, but I can see the paths are different really easy. So I want that graphically. So this is a prototype, but I think that this prototype that Embarcadero went on to add this to the product. But the idea is the bright green is where it starts, the NL. Intermediate light greens are intermediate paths, and the stop sign red is where it finishes. So I can see that Oracle started with this really bad join. Here is it's the same query, same map, but I start here, hash join in the middle, I end up back where Oracle started. So I can compare the execution plans really quickly and see why one's good and one's bad. Okay. Here's another really crazy query for me. It's super crazy. So there's two things strange about this query to me. One is the all the stuff here. See these O's? These are outer joins, and the big side of the triangle is towards the middle of the table, which means whether these rows exist or not is not going to affect the number of rows returned from that middle table. So really, when I join these in, doesn't really matter. They don't affect the running row set size. What affects the running row set size is this driving table. And then these other queries, this is the weird part. The other queries, all these guys, these are scalar subqueries. So the thing I circled over here is the select clause. And the way these guys decided to write this query, which might be fine, it's just unusual to me, is inside the select clause there's subqueries. So the fields are actually, some of the fields are actually select statements, which means that for every row returned from the outer query, each of those queries is going to get run. So here's the bottom half of the query, which doesn't really have any impact. These are all outer joins. Here's the driving table in the middle. And for each row returned from that driving table, those select statements are going to get run. Well, how many rows are returned from the driving table? There's a filter on it, and we can see that the running return row set sizes each of these select statements is 845,000. This would mean that each of those select statements is run 845,000. There's 4 statements run 845,000 times. That's a crazy amount of work, right? But this is where I get a little bit crazier. Oracle has a nice optimization. When there's a scalar subselect, and it gets run over and over again, Oracle will try to cache the values. So each of these 4 select statements that gets run for every row return, they're different select statements based on different fields. In this one, there's 12 different unique values that get put into it. Oracle can cache those 12 values. So once it's run that query for one of the values, if it sees that same value, it doesn't run the query again, it just returns the cache value. Oracle can cache about 1,000 values. It sort of depends on the data type and the size of that data. So basically, for these 3 tables, the 12 values, 825 and 845, it caches those. So it doesn't rerun them. Once it's run them once, that's it for that value. On the other hand, that one table, the input values are, there's 680,000 input values. Oracle can't cache it. That means that one particular select statement gets run over and over and over again. So that if we want to optimize this query, we found sort of the problem. Oracle can't cache it. It gets run over and over again. So how do I optimize that? And basically what I want to do is I want to pull out that select statement from the select clause and put it into a join. And it's a little crazy here, but so basically everything's driven from this one table, call it F. That was that middle table. And there was a select statement in the select clause here that's getting run over and over again. So on table X. So I pull table X down and join it. And then this is the way, it's a little bit crazy, but this is the way I can pull it out and have one join instead of rerunning that query. There's a total of 845,000 times. I'm jumping in some crazier statements, but I think this is, for me, this is how powerful the diagrams are, because attacking something like this without the diagram, I don't know how long or if I'd ever understand what was going on. In this final one, we're going to do something really cool, because Oracle will not optimize it the optimal way. So here's the query, here's the diagram. We see 3 filters. 1, 2, 3. The 2 on the either extreme, like we saw before, are basically returning the whole table, 99%. This table here, this filter here returns only 0.67%. So this is the only good filter. That's where I want to start. But after we start there, where do we go? Well, from A to C is a one-to-many relationship. That looks good. And you can see the values, the rows returned in black, 44,000. So that's where I would typically start. But there's something really interesting. This many-to-many join, which are usually bad, they don't have to be bad. F to D only returns 188 rows. You're like, well, that's really tantalizing. I wish I could use that. Because when we join the many-many, they can actually cross-filter each other. So if I started there, where would I go? If I joined up to C, I had the amplification problem where I actually cross joining all rows. There's like 3,000 rows here. There's like 3 million there, but the return value is 146 million. It cross multiplies the rows. So this might be a neat place to start, but it's not efficient to go up to C. It doesn't look very good. How about we join down? It's the same problem. If this is 1 million rows, and that's 3,000, but it returns 765 million. Or is it 76 million? So this cross multiplies again. That doesn't look very good. Well, what would be really cool was, what if I could just take the result set from D to G, it's only 188 rows, and join that with A to C, which is 44,000. All the other paths lead to millions of rows. The funny thing is, Oracle will never do this. Remember, Oracle will only start with one table, join in one more table. They'll never take 2 tables, get a result set, and join that with the result set from 2 other tables. Oracle won't do it. But we can force Oracle to do it. How do we force Oracle to do it? We run those 2 joins ourselves. I write a query to join from G to D. I write a query to join A to C. 2 different queries, and I join those 2 queries. So that's basically what I did. I just pulled it apart, joined A to C in that first query, joined D to G in this query. But be careful. Oracle will look at this thing, it'll pull it apart, and it'll try to go back to its normal optimization path. So I added a hint, no merge. I'm like, Oracle, don't screw with this. Do it the way I told you to. And whoops. So the first version took 4.5 seconds, over 1 million logical reads. And the second version did 12,000 logical reads and did it in 1/3 of a second. So this is the kind of thing I would never figure it out without the diagram. So I went a little fast today. I went from like some really easy diagrams and I jumped to the really hard diagrams. I probably should have done some medium diagrams in between, but I wanted to show the easy ones, sort of see how it works. And I want to show the hard ones to show it's really powerful. So related info, hints. I use the leading hint to just make Oracle choose the path that I want. I think I'll throw this in the next few slides if you have time. I'm going to show hash join hints and nested loop hints because I think they're confusing. What tools do I use? I use PowerPoint a lot of time, or if I have Embarcado's DB Optimizer, I use it. I'm going to talk about, there's tools that have graphical execution plans. You'll see it in Enterprise Manager. They're not visual SQL tuning diagrams. They're really nothing to do with it. I'm going to show, John Lewis wrote an article on using this method. It's pretty cool. I'll show you his query that he did by hand on pencil and paper, and I'll show you a DB Optimizer. And then if we have time, which I don't think we will, I'll talk about some detailed join ratios. So the leading hint, I've already mentioned, this is how I tell Oracle what path to take through the statement. Here's the hints I use. Leading works 10G and up. If anybody have a 9 database or older, there are a couple. You can't use leading on 9 or older, but you can use ordered, but that means you have to rewrite the order of this table in your SQL statement. 10's cool. I don't have to change the statement. I just change the order inside the hint. When I want to use nested loops, I thought I would give table 1 and table 2 in the hint. If I want to join table 2 nested loops to table 3, I would think I'd put table 2 and table 3, but that's not how it works. You just have one table, and it's the second table you find in the extending plan. It's the one that you look up the values into. That's what goes into the hint. And then use hash join is, I found this confusing. Use hash join. When you see a hash join in your execution plan, the table that goes into the hint is the first one. And the first table in a hash join in an execution plan is actually the one that you probe into. And then sometimes I want to force indexes. So indexes is the table alias and then the index name. And then no merge was what I used to tell Oracle to leave my query alone. Anybody use nested loop or hash join hints? One person. This might be overkill, but here I'm sort of explaining. If I say leading x, y, this is going to, the table order will be x to y, and the only nested loops hint that will make sense is y. Y is going to be the second table. If I said nested loop x, Oracle would ignore me. If I only do hash joins, it's the opposite. So I say XY, the hash has to be the second table. Sorry. The Y is the first table. Anyway, I find this stuff confusing. I try to document it. But if nobody uses the hints, then you can forget about it. I think this is interesting. Here's showing two execution plans compared to each other side by side. I find that unreadable. Let's look at that graphically. So I graphed out these two execution plans. So we have a filter here, many to one, many to one. Where do I start where the filter is, right? And then I want to go down and then up. But what do these two plans do? Green is where it starts, and it does a merge join between these two tables. And what's that mean? There's no relationship between them. That's going to be a Cartesian join. So this is a bad idea. This guy, we want to join down, right? This guy starts with green, does a hash join between these two. So he starts here, it's cool, but he joins up. That's bad. So again, I'm just showing the power of the diagrams. Like looking at the two execution plans, it would take me a long time to figure out anything wrong with them. But by putting them in a diagram, I can see it really quickly. Now, in lots of tools, you'll see the execution plan graphically. The execution plan graphically. I think this might be from Quest tools. I don't know. Most every tool has a graphic visualization of the execution plan. I can't really do much with this. What's going on here, if I do it with a visual SQL tuning diagram, is much easier to understand. What I can see is the order is the same. I join these two first. Same thing up there. I join the bottom two first, and then the top one. The only difference is this is a hash join and a hash join. That's a nested loops and nested loops. Looking at these things, it's hard to compare the two. And then finally, this is going to be an example from Jonathan Lewis. So Jonathan Lewis has a nice article where he takes this query and he discusses it for multiple pages in the article about what's going on. He ends up diagramming and coming up with an optimal solution. So I took this diagram and I dropped it in the DB optimizer. And just to go over what's being shown, on the bottom of each node is the filter ratio in blue. On the top in green is the number of rows in the table. And then on the lines is the number of rows that I return just joining those two tables, only those two tables. And with that information, we can actually find an optimal plan pretty quickly. We can also find a bug in Oracle pretty quickly. So one thing, there's an E here, so this is a not-exist. Sorry, it's an exist subclause. So this is going to get run separately from the outside. But let's graph what Oracle does. Here's what Oracle does. And the question here is anybody see a bug in this? So there is a bug. So there's a dark green on the left, that's a start point, and a dark green here, that's a start point. So it runs two different queries. So it runs the exist separately from the outer join, and then it ends up on this hash join where the red is. Now somebody noticed something really cool here. There's 0 rows returned here. This is not the bug, but it's something interesting to note. Once there's 0 rows, that's basically the end of the query. That means there's not going to be any rows returned. Anybody see the bug? I'll give you a hint. It's in this part. Okay, let's look at this part. So there's 3 tables. It's an exist subquery. It's going to run on its own. There's one filter here. And where would I want to start this query? I want to start the query on the filter. Where does Oracle start the query? The dark green is the start. Oracle starts up here. It should have started down here. And actually, as we make this change, it's a slight modification in the logical reads. Not a big deal, but it is an optimization. So I think about out of time. One thing I will throw out there is it's actually really well illustrated here. Sometimes what looks like a one-to-many actually filters out rows. In the worst case, it filters out all the rows, and there's 0 rows returned. So in this case, this happens to be the most powerful filter, 5%, 0.5%. But if I got that 0 over here, so this is a 50% filter, not as good. If that 0 showed up there, that's where I'd want to start. And we could improve, I think we could improve these diagrams by adding what's called the join filters. Does a join actually filter out rows or not? And that's the percentage. And so we don't do that in the diagram, but if you diagram it, you can add it. And so we can add a filter. If I join into detail, what percentage of rows how many number of rows do I return on average? If I join from a detail down to master, if it's not a foreign key relationship, there's only a unique relationship, that could actually filter out rows. If it's a foreign key relationship, we know that the value is 1. That for every row in a detail, that has to be a row in the master. But if there's just a unique index defined, it actually might not always return a row, which might mean it filters out some. So that's the join detail filter and join master key detail. You can get more information on that in Dan Tao's book. I think I'll sum it up there. So just a summary. Draw each table as a node, draw a line between each node, draw the one-to-many, many-to-many, or one-to-one relationship. Mark each table as a filter. If you only have one filter, that's where you start. If you have multiple filters, you have to find out which is the most powerful filter, and that's where you start. Once you know where to start, you join down to the masters when you can. If you can't join down, you join up. If you have many-to-many relationships, you need more information. You need to get the two-table join result set size. And then you start off with the smallest result set size. So something to note, I didn't when in these diagrams, I don't talk about table sizes. Really, I don't use that to determine the execution pattern. I just use the filter, how strong is the filter, and what are the two-table join set sizes. Also, I didn't talk about index existence. This method just finds the best path through the tables. But if that path needs to access a table via an index, and it doesn't exist, that's a problem. So I can find the best path. Once I found the best path, that'll indicate to me if an index is missing or not. If there's a join that doesn't have an index on that path, then I need to create it. So instead of using explain plans, use a visual SQL planning. And that's it. Next thing, in the next lecture I'm going to talk about, instead of using AWR reports, use top activity and average active sessions. But I'll talk about that more in the next session on Ash Masters. And that's it. Thanks.